Welcome back to part 3. So for this part, we're going to look at the idea of center of gravity. So center of gravity is an idea or at least a phrase that I think most of us would have encountered before in our day-to-day lives. And in this part over here, what we're going to do is to really take a more in-depth look at it from a physics point of view, from understanding what the implications are when we look at the center of gravity with regard to the turning effect of forces. So we know that objects are made up of many, many particles. And when gravity acts on an object, every particle of the object is attracted towards the Earth. However, we do not draw a single line of weight for every single particle. That's not practical. We do represent the weight of the particles by a single weight acting on a single point. And this point is the center of gravity. Up to this point in our free body diagrams, we've always been given or assumed that the center of gravity is in the middle of an object. However, we are going to look at how the center of gravity is found, and which this is the imaginary point where the entire weight of the object seems to act. It's very important that it seems to act on this point and that it doesn't actually only act upon this point. The weight does act on every single particle in an object, and that is very important to remember. Now, to consider a body hung freely from a string over here, we can see that every single particle in this body, we only represent a few, they are feeling, the weight from the Earth's gravitational field. However, based on where this pivot is, I'm just going to leave my highlighter here, we can see that some of the weights on the left, we have the blue arrows, they are exerting a moment in the anti-clockwise direction. Whereas the masses, the particles, they experience weight on the right of this pivot, all the red arrows over there, those are exerting a clockwise moment. So, if this object is at equilibrium, meaning that once it's hung freely, it settles into a position where it's at equilibrium, what happens is that all of the anti-clockwise moments about this pivot is equal to all the clockwise moments about this same pivot. And if we look at the idea of putting a single force, one weight, it must therefore be right underneath the pivot so that the line of action of the weight passes straight through the pivot, and therefore there is no perpendicular distance and there is no moment. So how can we find this center of gravity, the position of the center of gravity? For regular shapes with uniform density, the center of gravity is going to be in the middle. We see over here two three-dimensional shapes, a cylinder and a cube, as well as a ring. This could be flat, it could be three-dimensional, and they all have the center of gravity right in the geometrical center of the object. However, this center of gravity does not need to exist within the object. So for example, in this ring, the center of gravity would actually be this dot over here in the middle. It does not need to be part of the ring. So that is why, even though there is no mass here, there are no particles of the ring here experiencing a weight downwards, we draw the weight to come from the middle over here so that we can consider the center of gravity to be in the middle here for computation of moments due to the weight, for certain examples like that. Now, how do we then find non-uniform densities, the center of gravity for non-uniform densities or for irregular shapes? So this is a demonstration I did in class last week. So the simple way that we can do this is for a flat object. For flat object, what we do is we freely suspend it. So over here, I've got a pin and this irregular piece of cardboard has been suspended. Okay, it's freely rotating about this pin over here. So this pin here is therefore the pivot. So let me note that down, mark it out as being the pivot. After this, we also hang a weight on a string. Okay, so this mass over here that we are hanging is there because the string will be vertical. And this tells us the direction which weight is acting upon. So if this pivot over here allows the object to be in this orientation, what does that tell us about the weight of the object? It tells us that the weight of the object must be right underneath the pivot so that its line of action could be directly passing through the pivot. Okay, let me just redraw this to make it very, very clear. We have over here this being the weight. And then the line of action, which I'm going to draw in a different color just to make it easier to see, must pass through the pivot. So essentially what the string allows us to do is to show the line of action of the weight. However, we do not know exactly where the weight acts upon, only that acts upon this line. So in the next picture on the right over here, what we see is I've drawn a line, okay, that is aligned to where the string was, and I know the weight must act somewhere along this line. I don't know where it is, but it must be somewhere along this line. Okay, it could be, for example, now acting from this point or from this point. We don't know. However, what we do know is either of these two potential weights, okay, or any in between them, would all act in a certain way to create or to exert an anti-clockwise moment. So that is why I have to hold it with my fingers. You can see on the left side of that photo over there. Because if I do not support it with my fingers, what is going to happen? This will swing back into this original orientation with the line of action of the weight passing through the pivot. Right now, the line of action of these three potential weights all do not pass through the pivot, which explains why when you let it go, it will swing back. So what we do now is we repeat this process with another point. So I pick another random point, it could be anywhere on this 2D surface, and I repeat this process. And when I do so, I draw another line. Because what is happening over here is this tells me that the weight must be somewhere below my pivot here. Okay, sorry, let me do that in red just to make it very clear. So the pivot over here now must be directly over the weight because the line of action of the weight, which I will now do in green, okay, must pass through the pivot. Again, I do not know where along this line the pivot is going to, sorry, the weight is going to be. So it could be here, it could be here. However, earlier we already determined a very important thing. We determined that the weight must be along that first line that we drew. Okay, so it must be along this line over here. So therefore, the only logical conclusion is that the weight must be exerted from the intersection of these two lines. So over here, we can see that on the middle image, where I've highlighted, I've marked out, this is where the weight should be. So this is the center of gravity and where the weight is exerted from. So now I can very confidently draw a vertical line and state that this is the point in which the weight acts, and that now if I have the line of action and so on, okay, I can determine this is my perpendicular distance, and I know that it would cause an anti-clockwise moment. Now, finally, just to check Okay, you don't need to do this, but just to check that this truly is where the weight is acting from, what we could do is very simply pick another point. So I pick the third point here on my 2D surface. And then on this third point, I repeat the process. If I have found the weight, what it must mean is that the weight must again be directly under the pivot. And we do see indeed from this photograph very clearly the weight is under the pivot. My intersection points of my two lines are going to be under the pivot, okay, thus showing that that is the center of gravity. This weight here now has no turning effect because the perpendicular distance is 0 due to the line of action passing through the pivot. So this is a very simple way, okay, we can determine the center of gravity of a two-dimensional objects. We're not going to discuss how we can do so for three-dimensional objects because unfortunately, three-dimensional objects not so easy for us to do. It's not easy for us to suspend it or to draw lines through a 3D object. Okay, marking that out would be very, very difficult compared to a 2D object, and that is outside of the syllabus. So let's look at our worked example. We have over here a family portrait with certain weight, 50 newtons, hanging on the wall. If string B snaps, what is the moment created by the family portrait, meaning the weight of the family portrait, and what is the new equilibrium position? We may assume that the mass of the family portrait is evenly distributed. So, knowing that the mass of the family portrait is evenly distributed, that tells us that the center of gravity of the portrait is in the middle. Okay, so I don't know exactly where along this. I also don't have the height of the portrait, but what I can say is the weight is going to roughly be here. It is going to be 50 newtons. So W equals to 50 newtons. And if I draw my line of action, that tells me very clearly that it is going to be 19 cm from either side of the strings or 29 cm from either edge of the paintings. So what is the moment created by the family portrait? For part A, we know that moment equals to the weight multiplied by the perpendicular distance of the weight. So we can substitute this in very nicely, 50 newtons times 19 centimeters. Quickly convert that into SI units. And then what we get over here should be 9.5 Newton meters. Okay, so this is our new moments created by the family portrait. So for B, what is the new equilibrium position? So for equilibrium, what it means is the center of gravity must be under the pivot. Okay, it must be directly under pivot. And if it's directly under the pivot, okay, this is enough of an answer, but let's draw this out just to be very, very clear. String B has snapped, so our pivot is very clearly the connection between string A and the portrait. So what it's going to look like is something like this. Okay, not really the best drawing, but we see over here, this is where the weight is and is acting directly underneath string A because my pivot is where string A is connected to the family portrait.